Hey everybody, this is Larry. This is day 20 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. I am now in Brooklyn, just coming back from the gym, but really I'm just testing the mic. So let me know about the mic levels, especially when I'm outside, and also like the wind and everything. So yeah, all right, back to the problem. Yeah, hey everybody. So yeah, I'm still testing the mic. As you can kind of see here, maybe, okay, you see it? I don't know. But yeah, so I'm testing the mic. So hope the intro makes sense. I was just in Brooklyn and I was just trying to play around with it. So let me know what do you think about the sound quality as I'm still here. But yeah, let's look at today's problem. This is day 20, as I should have mentioned. I don't know if I don't remember if I did. Yeah, today's problem is 907, sum of subarray minimums. Given an array of integers R, return or find the sum of min of B, where B ranges over every contiguous subarray of R. Since the answer may be large, return the answer modulo 10. This is kind of a hard problem. I mean, it's kind of funny. I mean, I don't know. Depends on who you are. You may not be laughing. But first of all, let's we noticed the mod, so let's make sure that we keep track of the mod. But what I was gonna say is that this probably wasn't that long ago a hard problem, and now it is like a medium, right? But the idea here is that, okay, well, how many subarrays are there? There are n squared subarrays, and if we do it, that way, that'll be fine up to a certain n, and this n is going to be bigger than that, right? 3 times 10 to the 4, what's that? 30,000. 30,000 square is very big. Was it 900 million or something? Or am I short? I don't know. Either way, it's slower than you can, right? So then you have to try to figure out a way to, just do it in either n O of n or O of n log n. And here, I mean, I don't know which one I'm aiming for, but the idea with these problems is just to figure, for me anyway, is to figure out what I call contribution. I don't know if that's, it may not be a technical term, but what I mean is that, okay, let's say the number 3, right? What subarrays or how many subarrays is just the minimum element? Given the 1, how many how many subarrays have 1 as the minimum, right? So that's basically the kind of idea. You do it for every number. And of course, the way that you may think about it is, they're not unique. Okay, that's what I was looking for. That's kind of a hard problem. We haven't done it before, to be honest. I mean, I think the first time I done it, it still was hard, but it's still not. It's not impossibly hard, but it is definitely very difficult. Like I could imagine I spend an hour on it if I haven't done it before, but have the same knowledge that I do now, but just haven't done it before and have the same idea. Yeah. So I think for this particular problem, it is important to kind of be very precise with how you want to do it. So let's say the numbers are unique, right? Are they unique? No. Okay, but let's say the numbers are unique now, so then we can play around the idea, right? Then what are we trying to do? Well, then and now we're trying to look at every element and see what are the smallest thing, right? And so, or how many arrays are there such that this is currently the smallest number? And we can kind of figure that out a little bit. This is kind of like, it's not, I don't think this is combinatorial per se, but the idea here is that, oops, I'm going to add just some numbers for fun, right? So let's say you have something like this. What I would say is just what I call the degree of freedom, right? And what I mean by that, let's say we're looking at number 1 for now. Oops. And we're saying, okay, well, how many of them have 1 as the minimum number as a subarray? Subarray is different than subsequence, but today we have subarray. And on the left, that means that we can. Well, 1 is the smallest element in the array, so that means that on the left you can go any number of elements, right? And then you have this degree of freedom to the left, and then this degree of freedom to the right, right? And then the idea here is that, obviously this subarray has to contain the number 1 to do it. And then the idea here is that on the left, what are the possibilities, right? Well, the possibility of it is that it can start at 3 and then just go to 1, or just 1, right? So it has, so on the left side, maybe I'll put it here. Oops. You have 1 number and 2 degree of freedom. What about on the right side? On the right side, okay, there's a lot of type. So you can have no numbers. You can have 1 to the right. You can have 2 to the right. You can have 3 to the right, dot, dot, dot. You can have all the way up to all of them, right? So, and, you know, there's no, because this is a subarray, you have to, these are the only possibilities to the left and to the right. So that's how we get the degrees of freedom, because you can choose on the left. You have 2 things to choose, like 2 ways to choose on the left. And then what is this? I didn't count, but yeah, but just, you know, 0, 1, 2, 3, 4, 5, 6, so like 7 ways maybe. If I'm off by 1 on the counting, you know, it is what it is. But on the right, so that means that now there are 2 ways times 7 ways. So that means that there are 14 ways. 1 is the smallest number on the subarray, right? And that's basically the idea behind this, right? And you can kind of repeat it for every number. So let's say now we're doing 5, and when we're doing 5, yeah, okay, fine. When we're doing 5, we have 0 degree because you can't choose any length. But on the right, you have all 4. So then, well, 3 numbers, 4 possibilities. So then now 5 is minimum of 4 subarrays. And that's basically the idea. And then now with that framing, what are you trying to do, right? What are you trying to do now is for each number, get the next number that is smaller than this number to the left and also to the right. And that's pretty much it. Or that's pretty much the idea about solving this problem. Again, this is still dealing with unique elements, right? So this is still a little bit tricky because, well, let's say what happens when they're not unique. And these are the things that when you're solving these problems, or when I'm solving these problems, these are the things that I play around with to kind of go through it in my head before actually coding, right? Because it does change the problems sometimes, and in this case, it does enough, right? Let's say you have 2 1s, right? Then what happens with this degree of freedom thing? Well, on the left side, you can say that there's only there's 1 way to choose on the left, same thing. And on the right side, you could also say the same thing, right? However, now if you do the same thing on the 1 to the right, let's say now we're using this one, you're going to double count, because now if you just do it naively, you may say that on the left you have 3, 1, 2, 4, 5, 8, 1 as one of the sequences, for example. And you know, you can even use periods instead on the left side, dot, 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 right? And of course this overlaps because this sequence is already included in one of the 14 sequences that are here, right? Because it just means that we choose 1 to the left and whatever it is, like 5 or 6 to the right, right? So yeah, so now we're double counting. So how do we get rid of double counting? So there are a couple of ways you can think about it, for sure. The way that I think about it is just by breaking the symmetry. The symmetry being that, you know, we're double counting because we're going to the left and the right the same. The way that I do it is by breaking the symmetry, which is that we don't treat the left the same as the right, so that another way of phrasing it is that it's just or another way to think about this is just about establishing a tiebreaker, right? Meaning that let's say you have this one and this one, and they both contribute, or they both want to contribute to the final answer, with the minimum being 1. Then only one of them can do it, obviously, otherwise you're double counting. And you know, and in an arbitrary way, or the way that I'm doing arbitrarily, is just to choose the one to the right to hold it, right? That means that when we're counting this one, we don't want to count past this one, so that when we are up to this one, we can go back and count this one. So that's basically the idea, is breaking that figuring a tiebreaker and then breaking that symmetry in establishing that tiebreaker. And that's pretty much it for the double counting. And as a result, it becomes, on the left, find the next number that is smaller than 1, and on the right, find a number that is 1 or smaller, right? So it's now a equal than and less than on the right, and equal to, or sorry, less than on the left. So that's basically the way to think about this. And now we have converted this problem to another problem. Now we have to figure out, okay, what is the next, or the previous, maybe, or the closest previous, or this is looking on the left, index that is smaller than, or, well, in this case, just smaller than, or equal to this number. I think on the left we go the same, right? So yeah. Oh wait, no, because equal to, we can yeet it, if you will. So it'll just be smaller than, right? And then also, what is the next, closest next index that is larger than or greater than or equal to this number, right? So now we kind of distilled or converted the problem into these two problems, and of course these two problems are very similar, obviously. And there are a couple of ways you can think about doing this. This is kind of a man, I am kind of tired, to be frank. I just went to the gym, as and my gym session today was 3.5 hours, so I'm kind of a little tired. Also, I should double check the mic. I hope the mic is working. Otherwise, man, I am not going to be super happy. But yeah, but the idea, and there are a couple of ways you can think about doing it. I actually don't know the right way, but I feel like there is another way that is more inefficient, but still correct. But I forgot how to do it that way. That I usually, in the past, that's the way that I used to do it. But today I forgot. Like there is a slightly inefficient way with sorted list, and I should like practice both. That's why in my head I'm trying to think a little bit. So sorry. And you can always fast forward if you like. But give me a second to think about it. How do I do it with sorted list? I guess with a sorted list, it just becomes sliding with, no. I guess. I mean, I guess there's a binary search answer, but is there? Man, I'm so bad at it today with that. How do you do it with sorted list? Sorry, friends. I am recording these live, so sometimes if you're impressed by how am I recording this live, also sometimes know that because I am recording these live, I am going to have some brain farts, like this particular one with sorted list. How do I do it? So I know how to do it the other way, but probably the more correct way. But I'm trying to think, because there are problems where one is easier than the other. So I want to, at least, like, this is my personal goal. So thank you for kind of going on this journey with me. But for my personal goal, I want to be able to do it both ways. And I usually in the past have done it with the sorted list. That's why I'm trying to figure out why I'm struggling a little bit. Maybe I just don't know. All right, let's do it another way, and I'll have to read up on it later. But basically the idea is going to be a solution where you basically look back. And the idea behind this look back solution is just that, okay, this is this incrementally built data structure using a stack or an array so that you can take advantage of things you already know, right? So for example, you have 3, 1, 2, 4, 5, right? And then we build this one at a time. Oh, this is array. All right, let's just say we have this array, and we're trying to build the answer one at a time, and we'll look at only the small thing for now, the left side, right? So that means that for 3, the smallest to the left is going to be infinity. Okay, no answer, right? Or 0, depending on how you want to say it. And then 1, again, nothing, so that's good. But now there are a couple of things, right? Now that we have this 1, what does that mean for the future? Well, in the future, there are only 3, not including the Leetcode signs. Let's ignore the Leetcode for now. But there are only 3 cases, right? They're only greater than 3. They're between 1 and 3, which is a 2, I guess. But right. So let's say it's some x that comes in later, and then 1 is x, right? So something like that. Right, so these are the 3 possibilities of the next number coming in. And what happens? Well, if x is greater than 3, that means that, let's say we have some number x that is greater than 3. What does this mean? Well, it doesn't matter, because if x is greater than 3, then x is greater than 1, right? Obvious reasons. Or just, you don't even have to be obvious reason. There's no reason. It's just obvious, right? And then the idea here is that, well, in this case, 3 will never be the answer, right, for the future, because if x is greater than 3, then the answer would just be 1, because that's closest, right? Let's say x is greater than 1 and less than 3, so x is 2, really. If x is 2, well, 3 is still never going to be the answer, because 1 is smaller than 3, right? So, and closer, which is the more important. Well, they're both important, but yeah, that's another part. So that means that if x is between 1 and 3, it will not, the answer will still be 1. And if this is less than 1, then, well, you have no answer, but 3 will still never be the answer in this case if x is less than 1. Let's say x is, I don't know, -5, 3 will still never be the answer. So therefore, in this way, you can reason that, so that when we get an incoming number and we're processing it for the future, 3 will never be the thing, so then we could remove it for future considerations. Now we have a 2. 2 can be the answer, because in this case, let's say you do that analysis again. Can 2 be, so now you have and yeah, let's pretend that x doesn't have to be an integer just for the purpose of whatever. So we have some x, and okay, if x is 5, then what happens, right? Well, then 2 is the answer. If x is 1.5, then 1 is the answer, actually. And obviously, if x is less than whatever. So we keep all these 2 numbers because everything is possible. And this happens to be a 4, so we keep the 2. So then now the same thing, right? So we have a 5. What happens? Well, if we have a 5, then the next answer is going to be 4. But if we have a 3, then the next answer can be 2, right? And also if we have 1.5, then the next answer can be 1. So they all can be possible. So we don't have to, we don't do any removal. So now we have to add a 5, same way we add an 8. And then now we have a 1. Then what happens? Well, with a 1, there are a lot of possible, you can break down the ranges if you want, but 8 will never be the answer again, so you could pop it. 5 will never be the answer again, right? So we could pop it. 4 will never be the answer again, so we could pop it. 2 will never be the answer again, and then we pop it. I forget how we do the Leetcode signs on this one. So smaller than this number, so it has to be strictly smaller, so even this number, we pop it, right? So that's basically the idea about these things, because basically we're eliminating things that are impossible to be the answer. And if you kind of look at this, of course, if you kind of look at this, the way that we do it, if you get a smaller number than, say, 8, then you remove, let's say we have a 7 next, then you remove 8, right? As a result of how this algorithm works, it turns out that this thing is going to be monotonically increasing, right? Or they're just increasing. And that's kind of like a, I don't know, as I always describe it in these problems, this is a property, not the thing. So like sometimes you read this problem or similar problems and they're like, oh, it's just monostack, and monostack usually just mean like monotonically. Man, I'm blanking on words. English is hard. Monotonically increasing or monotonically decreasing stack, and or like a monostack. And you're like, well, what does the increasing or decreasing thing have to do with it? And the answer is, it's an emergent property. It's something that comes up as a result of it, and itself it's a property, but it's not interesting in the way that this can be done, right? Like just knowing that it is increasing doesn't mean anything without context. So that's why I kind of hate the term, or at least I hate naming the problems with these terms, is why. All right, so yeah, that's basically the idea, and you can also do it in reverse to get the bigger number to the right, and you just sum it all together. That's pretty much the idea. We've talked 20 minutes going from 0 to this, so now it's time to finally code this up, right? So okay. So then let's just say we have left is equal to right? So now for x in array, and maybe we can say, yeah, maybe we can define this as infinity and then like a, I don't know, -1 maybe? I don't know if this is a good number, but we want to keep track of the index, right? So then here we want to remove impossible answers, right? And an answer is impossible if it is smaller than the current. Oh, maybe this should be -infinity then. Oh yeah, because then by default, no matter what, that'll be your smallest number, or like being the borderline. That's just the base case. But yeah, remove impossible answers. So while length of left is greater than 0 and left, so this is the top of the stack or the rightmost side of the array, if you prefer that. And then now the value of it, and this is just the, so this is the value, and this is the index of the array element. I think -1 makes the math easy, but maybe it's 0. I actually don't know about this one. Didn't trace it through yet. We'll go for it together. But yeah, while this number is bigger than x, and actually equal to, right, because that means they're not possible anymore, then now we left that pop, and then at the end we append x and an index. I actually should enumerate this so that we get the index. Right, so that's the part about removing answer, and then this is actually save current array element for future, I don't know, lookup, I guess, right? But actually I forgot to actually do the more important part, which is the counting, right? So then now here, oh no, I guess we have to do this first. Yeah, and then now the next number that is smaller than it is just going to be the number that's on top of the stack, because you actually remove all the numbers that are bigger than it, and every number can only be removed once, right? So yeah, so so this is the left stack, but actually what I want to do is calculate the index, right? So basically we're calculating the degree of freedom on the left side, which is what I on this part of it, right? So yeah, so I want to save it down. Left degree, I don't know how I feel about that, but yeah, degree we want to append, which is, so then now the top will contain the value, but also the index, right? So basically the degree of freedom that we have for this answer. So this is the index, this is our index, is the current index. So okay, so top index is equal to left of -1's 1, and keeping in mind that because this is -infinity, we'll always have more than one element. So I guess I technically don't need this, but I don't know, I'm always just it is, you know, like muscle memory and memory. So top index is that. So then now index minus top index is going to be the number of degree of freedom, right? Plus 1, right? Because you can also choose 0 as a degree of freedom, meaning nothing from the left side. So is that true? Maybe this is 0 then, I think. Maybe. I'm trying to think in my head what is the right default. We get the index. Oh, oh yeah, yeah, okay. So the next, okay, I see. So the next number that is smaller, you don't get to choose that number. So it is not inclusive, it's exclusive on the left bound. So that's why it's index minus top index. Okay, that makes sense. And then now we do the same thing on the right side. The difference between the right side and we'll just reverse this. But so basically we're going to the right from to the left. But yeah, the difference between the right side is that is this part, right? Is that if you're looking to the right, if you gain an equal element, you don't pop because it is not considered impossible answer. In fact, if it is equal, then that's where you stop anyway. So yeah, so that's why. So this is the key thing: less than equal than this. Otherwise, you would just have, one function, right? I mean, you still can, I guess, but it's just like more annoying to write. And then now, of course, we have to reverse right degree. And then now, yeah. So then now so n is equal to length of array. And we just sum up all the things. So then here now, we have left degree of freedom of I times right degree of freedom of I, right? So that's the number of times array sub I is going to be the minimum answer. So times a sub I, that's the number of contribution. And then we just add it all together. And of course, we have to remember the mod. And that's pretty much it. Hopefully. What did I? Oh, why is there? I don't know what I was thinking here. But yeah, so looks good here. I mean, maybe I have some silly mistakes, but that's fine. Good enough to submit. And yeah, and that's pretty much it. 13 90-day streak. Apparently I didn't do that it didn't feel like that long ago, but that's been a year and like 3 months. Time really flies. I'm getting old. But yeah, as you can see from this complexity, it's going to be linear time, linear space. I mean, the stack can only be linear. Even though it's a loop inside a loop, each element in the stack or the array left can only be removed once, so it's going to be amortized linear or amortized constant per operation, linear in total. So this is going to be linear. Same thing here. This is just changing one sign and doing reverse. And yeah, and this is also obviously linear time, and we just have linear space for the stacks and the degree things. And that's it. That's all I have for this one. Let me know what you think. Let me show you the top of the code. And oh yeah, and the other thing is that we have to reverse. Just remember to show you. And that's pretty much it. I mean, this is the total, and then I have just like all these notes with the total at the bottom. Maybe I can move this up actually. I don't know. It doesn't matter, right? Anyway, that's all I have for this one. That's it. Yeah. Stay good. Stay healthy to good mental health. I'll see y'all later and take care. Bye bye.